The work breakdown structure, that's a specialized structure. We could fill a wall, by the way, of all the things that needed to be done to go to the moon. You have boxes showing this, boxes showing that. Some of them would be colored red because we didn't have whatever we needed. Could be insulation, could be a screw of a certain tensile strength. If they're on schedule, if they're behind schedule, if they're ahead of schedule. If something is falling behind that we need taken care of. Sometimes you put an incentive fee on a contract, change it so that things happen, and that's what change order systems are. Basically, that is the contracts that NASA allowed for changes as you made progress. We saw something else need to be done. We wanted to be able to change the systems and change the contracts, and NASA worked very hard to make that work. KT stands for Kepner-Trego and other problem-solving systems. Kepner-Trego is a deviation analysis system. We found out what happened to Apollo 13 when all the evidence was gone. We had an oxygen tank blow up on the way to the moon. The astronauts were saved by using the lunar lander as a lifeboat. We went around the moon once, took them back to Earth. But we needed to find out what happened, and when the capsules ended up entering the atmosphere, they all burned up. So we had no hard evidence, and yet, using this deviation analysis process, we were able to figure out exactly what happened. This is just an overall gross work breakdown structure for water on Mars. You're going to see this later on when I start talking about Mars. And these are all the systems that need to be done, and each of these little blocks has hundreds of blocks in addition to it describing all the pieces that need to come together to make every one of them work. Now, you heard before about President Trump saying going to the moon. Here he is. SPD-1 is Trump's first space directive #1. And here he is. Remember Jack Schmitt, the astronaut, was full of dust and dirt? Right now. Okay, he's growing a bit. He ended up being a senator from Arizona, I think. Oh, no, New Mexico. He's giving President a little spaceman. Next to him is Peggy Whitmore, is a woman who spent more time in space than any woman alive. And in the back, this guy right here is Buzz Aldrin. Buzz Aldrin is the second guy to walk on the moon. And they're all in there witnessing President Trump saying, NASA, we're going back to the moon. And I happen to think it's a very good idea for a lot of reasons. And I'll talk about those in a minute too. So that's what President Trump wants us to go. This is the part you see. This is called near side. This is the other side of the moon. Nobody from Earth can see this from Earth. It's called lunar far side. People refer to it as the dark side of the moon. That's wrong, it's not, because it gets light half a month and it gets dark the other half a month, just like everything else on the moon. But it is far side. It is different in character. So guess what? The Chinese decide we're going to get there first, and they did. This is Chang'e 4, and now to get to lunar far side, and this is going to be a little bit more complicated than you'd probably like to hear. Okay. First of all, remember during Apollo 8, we could not communicate with anybody when they were on the other side of the moon. Radio waves, we have not figured out how to penetrate the moon. So what we need to do, if we're going to do anything on far side, is put a satellite in Lagrange 2 on the other side of the moon, where this point rotates around the moon once a month. So it always stays there. And what the Chinese did is they put a satellite around there in a circular orbit like this. You notice from Earth, you can always get a signal to this satellite, no matter where it is, and the satellite can then transmit to the dark, I almost said it, dark side of the moon, or lunar far side, okay? So then, when they do have a lander on the far side, they can direct the lander, they can communicate with it, and I'm going to show you some of those effects. They had a lander, not only had they had a lander, but they also had a little rover. I think it's called U2. And I'm going to show you a video clip, and I hope this can play here. Let's see if I can get this to go here. If I hit the arrow. You're going to see the actual landing of the Chinese lander on lunar far side if this thing will play. I'm pressing on the arrow. Maybe I can do it down here. No. See if we can make this thing work. This should play as a video clip. There you go. You did it.
All right.
Okay. Now watch what happens here. The lander is actually heading down toward the surface, and these pictures are being relayed back to that little circling satellite. You notice the horizon is getting shorter and shorter as it comes in for a landing. So now this crater is going to dominate the horizon, and we're getting very close to the surface. And all this is being controlled by the Chinese controllers from Earth because of that satellite on the other side of the moon.
But what speed?
Excuse me?
What speed is it going? Speed, how fast is it going?
Oh, it's landing, well, it's going to slow down and slow down as it comes in, but it's coming in at about maybe 20 meters a second at first. And it's going to slow down to 1 and 2 meters a second. But see, here's a problem. Where it's going right now, you can see a couple of irregularities. It's coming down and slower. And now you see that it's beginning to head to some hills and craters right here. They can't land on those hills. So the controllers stopped it right there, put the brakes on, and then made it land a little bit further over. Right? And this could not be done without that satellite on the other side of the moon. If it had landed on that hill, it would have tipped over. So now it lands, it's coming down quick, bang, it bounces, and now the dust is going to settle, and you're going to see a tack-sharp picture of the ground right where it landed. So about 1.5 billion people have seen this video clip. Very few of them are in the United States.
Yeah.
This should have been shown on television everywhere in America. The same way, of course, we were showing our moon landings. But they didn't do it. And I think this is a magnificent achievement, landing on lunar far side. And it got back page coverage.
What's the reason they didn't do it? What's the reason they didn't show it?
Well, that's the problem. Anyway, so remember that hill it was going to land on? Here it is. This picture was taken from its little rover. So instead of landing on the hill and tipping over, it landed in a good place. This is what it looks like. Now this took that picture. This is the U2, and you can see the little tracks it's making as it's exploring, and it's going to drill into the surface. And yes.
About how big are both the lander and the rover?
Oh, much smaller than the lander that we had people in. I'd say, I think the original could fit on this table. All right, so, and this is a very small rover, but it pedals around. It's got little, they've learned from us, okay? They don't have rubber tires or anything. They have wire mesh wheels. And we had that on Apollo 17 and Apollo 16 in our rovers. And this is one of the real neat things about space technology is that we can learn from each other. We can help each other's space programs. We have a problem in this country. We have an amendment that I think it was a senator from Texas stuck on an appropriation bill that prevents us from giving technology to the Chinese, because we thought they were stealing from us to begin with. And that's okay, if it's done for peaceful purposes.
Where are those pictures being taken from?
This was taken from the lander that you see over here.
Why is
This is the camera right here.
is it coated with gold?
No, it is gold foiled aluminum foil, very, very thin. And it's to protect it from heat from the sun, which may adversely affect some of the instruments inside.
Yeah.
Our lunar lander had it too, by the way.
Out of what?
We had gold foil on our lunar landers also for the same reason. Basically, it's a cheap, easy insulator because it reflects the sunlight and will not allow 250-degree temperatures to ruin instruments. So if you have a camera in here, you want to protect the camera, insulate the spacecraft. So this camera took a picture that you see right here.
Who took that other picture?
Yeah.
The rover.
And the rover took the picture
Yeah.
that you see right here.
Us?
Pretty neat, huh?
They took pictures of each other.
Right,
Yeah, okay.
yes.
Just really quick, what's the relay time between, like, from Earth to,
A minute and a half. It takes light that long to make the round trip. So that's why you could see them as they were coming in. They had to stop the spacecraft. And then about 3 or 4 seconds later, they figured out where they wanted to go, put the instructions in, and let it land.
Was the problem with the rubber tires that it would bounce?
Well, no, rubber tires would explode
Oh, okay.
unless it was solid rubber.
Okay.
And solid rubber is heavy.
No.
So on our rovers, you'll see another picture of one in a minute. We use wire mesh,
Yeah.
like you see right
Yeah,
there.
the rover you mentioned, yeah.
And it's lightweight, has traction in dust, and if you don't have fenders, it kicks up dust too. So, all right. This is where NASA. There's different ways to go to the moon. President Trump wants to go to the moon. The way we did it first is we sent a rocket straight to the moon. It says no supply chain. Okay, this is what we call Apollo architecture. Went straight to the moon, actually went in orbit around the moon and then landed. The program that President Trump has signed on to, and I think NASA thinks is going to work, and I believe it too, is a space transportation system architecture, where LEO means low Earth orbit. And here we have, this is the International Space Station. These distances are different, by the way, all right? And we want to put a lunar gateway in orbit, and that gateway would then be a way station for astronauts and equipment, material, supplies to get to the moon. It looks kind of like this. Here are our rockets, the big rockets that get off of Earth. The lunar gateway will look like this. And then you would use that same gateway to go out to Mars. That's why Buzz Aldrin was all excited about being there. And I'm going to talk about Buzz in a minute. This is what the lunar gateway supposedly would look like. It's a mini space station that is in permanent orbit around the moon. Does not need to be occupied, but can have be occupied for certain missions. And it has enough room to store oxygen, store fuel, store food, and other things that people would need using that gateway. So here's Jim Bridenstine, the new NASA administrator, describing how the Gateway project would work. Here's another picture of the rover. You can see the mesh tires here. We want to do a lot more on the moon now. We want to just go there, come back. We want to basically create structures there. We want to go to the lunar South Pole, where we believe we will find water. We believe we're going to find helium-3. We can take that back to Earth, do very, very easy fusion to create energy. And that's the reason that the Chinese want to go to the lunar South Pole too. We do believe there is water in those craters. We need water, and water is very heavy. To transport water to the moon requires an awful lot of space. If I have my hands like this, and I have a cubic meter of water, anybody want to guess how much it weighs? Now, some of you know, because I've already said it in the other lecture.
1,000 pounds?
1 ton, 2,000 pounds, right? If it's ice, if it's water, it's 2,240 pounds. Very, very heavy. There's a lot of rocket fuel you need. Now, if we could find water on the moon, we have saved an awful lot of transportation costs. Now, you see, it's more than one rover here, and we have a lot of things we can do on the moon. We need to do it. This is a space tug landing, by the way. What's a space tug? The space tug is a vehicle that we put into orbit and never comes back to Earth. It's ugly as anything because it doesn't need to be aerodynamic or slim and sleek. It doesn't have to have fins or anything like that. It's just meant to go between low Earth orbit, the gateway, and the moon itself. And that's why I call it a space tug. It can take materials back and forth. We need a fleet of those to make this concept work. So I told you I was going to tell you more about Buzz Aldrin. Here's Buzz Aldrin. All right? Buzz, second guy to walk on the moon. He's standing in front of Stonehenge in England. And his T-shirt, you can read the words here. You can read them more clearly here. This is a test pilot speaking. And by the way, you notice the flourish here is in a different direction than the flourish in the regular NASA logo. So Buzz, and you can include me in there, want to turn the agency around. We want to have a new direction for the agency. This is Phobos, the large near moon to Mars. This is Deimos, the other smaller outer moon. Phobos is a very fast-moving moon. It rises and sets 3 times in a Martian day. Goes around a planet 3 times in one day, really fast.
Oh.
We go to Phobos, we're going to save a lot of rocket fuel. Because when you head into Mars's gravitational field, you have to put the brakes on and slow down, but we can catch up to that fast-moving moon and get out to Phobos. And when we want to come back to Earth, we go from the other side of Mars, and we get a kick back to Earth, right? Yeah. So very, very good reason to go to Phobos. How are we going to do that? Well, this is out of the Hollywood movie, The Martian. Some of you may have seen it. Actually, I like the movie very much, but there's some big flaws. You see these, first of all, the one thing they have right, this is a circulating thing. The astronauts sit on the outside of the circle. It spins. You get artificial gravity, which means that your astronaut will live a lot longer and be a lot more comfortable. Because we have found that being in a free-fall, weightless state deteriorates bones, is very, very poor for health. That's why Meg Whitmore was on there, a woman who's in space for many, many days. When some of the astronauts get taken off of the International Space Station and land on the ground in Russia, they have basically a wheelchair waiting for them. Yeah. They are so weak, the bone structure has been deteriorated. They have to regain that strength. Their muscles deteriorate. So if you have artificial gravity, that's great in the spinning part of the spacecraft. What's the big flaw? These big giant windows. No, you don't need windows in the spacecraft. The structural integrity would be compromised. All you need is a tiny little peephole and a big flat screen TV inside the spacecraft so they can see what's going on outside. So this makes for great movies in Hollywood, but you don't want to build a spacecraft that looks like that. Okay.
Can I, one question?
Yes, of course.
What do you, what was your reading on the Scott Kelly and the other brother results from a few weeks ago? Because they said that he had surprisingly little big damage to his health system or something like that. Yes, but there were detectable differences in the two twins. And not just in bone structure and muscle structure,
but in cognitive ability too. And it was discernible, it was measurable, and that just tells you that we need an artificial gravity method for long interplanetary voyages. We get to the moon in 4 days. It takes a half year to get to Mars. And then you got to stay on Mars in that area for another 2 years before you get back. Yes?
Beyond gravity, there are electromagnetic, geomagnetic things that affect the human, that we have on Earth that we won't have in space, that also have to be replicated.
There's lots of other things. Cosmic rays, for instance. The Apollo 17 astronauts, when they closed their eyes, they saw flashes. We had a cosmic ray detector on the spacecraft. They matched the times that the astronaut with closed eyes saw the flashes. So we knew that there was interaction between cosmic rays and the health systems of the astronauts themselves. We don't know yet what long-term exposure to cosmic rays is going to get us. The astronauts that are on the International Space Station, they're in very near-Earth orbit. They are already shielded partly by Earth's magnetic field from many cosmic rays. The ones that were going to the moon weren't. If we go into Mars, they're not shielded either. So there's a lot of things that we still have to find out and figure out before we do this. Yes, ma'am?
There's been a lot of talk since we want to go back to the moon that the computers we were using the last time we were there were the size of this room, and now they're the size of basically your cell phone. How is that going to change the rockets, what we can take? How is the improvement of computers going to change?
You basically said that it's going to get a hell of a lot better and a lot easier. Because our computers on almost a yearly basis are getting stronger, faster, smaller. Now, like I say, what I have here in my little iPhone could run rings around what the landing computer had on the way to the moon. In fact, Armstrong had to override it because it got overloaded. We had about maybe 20 seconds or so worth of fuel left, and the computer was giving warning signals and not functioning fast enough. They had to input 5 numbers in order to change the instruction set of that computer. It was all manual, no screens and nothing like that. We managed the moon landing because we had a test pilot who was at the controls and knew what he was doing. I have a picture of that computer somewhere, but I don't think it's in this presentation. So I apologize for that. It was a good question.
It's going to change the rockets a lot, I would think, and what we can take up there.
Yeah.
Oh, yeah. Lots has happened. The fact that the addition of computing power and ability was, I think, generated from NASA, but has spread all over the world. NASA's not just the only place that you get better computers these days, but we started it. We know a lot about Mars, okay? We've named everything on Mars. Of course, we named it with Earth names. This is Arabia, this is Eden, this is Utopia. Give me a break. All right? But we have a pretty good idea where to go. Here's what the mission would look like going to Mars. First, you send 2 giant supply vehicles. And you do this happens to be one scenario, and we send these off in 2035. It takes 202 days to get to Mars. In my view, we need to get into Phobos, not Mars, okay? So you have materials that allow astronauts to live. And then 2 years later, you send the astronauts there. You send them there, it takes the same time to get there, but they have the supplies already waiting for them. Here's Phobos. This is where I think they need to go. Phobos is a fascinating one. Again, we'll go to a planet 3 times in one day. Look at these chains of meteor hits. Geologists go crazy about this. That's why Jack Schmitt was so happy sending next to President Trump saying, yeah, go back to the moon and then go to Mars. This is either frozen carbon dioxide or frozen water, probably both. So landing in Phobos, we're going to learn a lot. We've already mapped out where we want to go when we go there, if we go there. So these are 10 points that they want to look at. And we can have a rover on Phobos.
So those streaks,
It will look kind of like this, yes?
I'm sorry, you said the streaks were from meteors?
No.
That's what I said.
These are meteor hits,
The streaks?
not just one meteor.
Yep.
So even there must have been a chain of meteors
Yeah.
that this moon intercepted and shot it like a machine gun, like that. We believe these are all at the same age. And this is a different set, some of them are bigger, some of them are smaller. There's an awful lot that we can learn about the nearness to the asteroid belt that Mars has and Phobos has, and its effect on the planet itself. I believe that they're from the asteroid belt, but I have no idea. Maybe we'll find out. That's why we ought to go there.
Yeah.
We go there to learn, okay? This is one conception of what it would look like. An SEP is solar electric propulsion tug. It allows us the astronauts to get into it and go to a different part of Phobos. Phobos' surface to do more exploration. The Orion is a redesigned capsule, which is larger. It looks a little bit like the Apollo capsule, but has been improved. This is just in the concept stage at this point. But this is what Mars looks like from Phobos. Remember I said it's a close, very close moon. We can learn an awful lot about Mars by going to Phobos. By the way, today, we can't take off from Mars. You go down to Cape Kennedy and you look at the gantry cranes and the fuel depots that we have there. None of that exists in Mars. Mars is a planet. It's not like the moon. The moon is low gravity. Phobos is even lower gravity. These guys will be able to walk 100 feet per jump. Imagine jumping in the air and landing 100 feet away. And you're going to do it really slowly, too. So Phobos is weak gravity. Mars is not. Mars is a big planet. We can't take off from it now. We can set up a permanent settlement. I'm going to talk about that in a minute or so.